To share my recent work here. Here today I want to talk about the transition from fractional diffusion to normal diffusion. First of all, I would like to introduce what is those three different kinds of diffusion: super diffusion, subdiffusion, and normal diffusion. Actually, this full picture is for you can see my mouse, right?
Yes, we can.
Okay, good. Actually, this full picture is an explanation about subdiffusion. For when there is a parameter here called alpha. When alpha is 1, it's the normal diffusion. You can see the particles just spreading out. When alpha decreases, we can see that the spreading becomes slower and slower, which means for subdiffusion, the spreading behavior for particles is much slower than for normal diffusion. Well, these two pictures is a typical trajectory, a comparison of the trajectory for super diffusion and diffusion. For super diffusion, we can see non-negligible number of long jumps. So the particles can jump from one place to another place quite quickly. Well, for normal diffusion, we don't see this. So for super diffusion, if we look at the particle spreading, it's much faster than the normal diffusion. Actually, all these three different kind of diffusion can modeled by running one process. It's just for different diffusion, it's just a particle wait in one site for some time delta t, then jump to its neighboring site which is delta x. The distance between these two neighboring sites is delta x. This delta t and delta x, both of them can be some probability, can be some random number with certain probability. If we want to study these three different kind of diffusion, then there are two typical statistics that one can do. The first one is the Path-Nernst distribution or the waiting time distribution. Basically, the Path-Nernst distribution is we just follow the trajectory of the particle. Follow the trajectory of the particle and record the path length of the path length of two successive velocity change. Then plot the probability density function of it. For single diffusion, we can see there is an interval that the Path-Nernst distribute. If we put it in a log plot, then the Path-Nernst distribute there will be a linear part for this Path-Nernst distribution. Well, for normal diffusion, it will drop directly. So, the other statistics that people would look at is the time and mean square displacement. For normal diffusion, it's linear relationship, while subdiffusion is slower than linear, while for super diffusion, it's faster than linear. Actually, for this process, we can write down a diffusion equation for it, for a PDE for it. Just the operators are different. For super diffusion, it's the Laplacian operator has some power, while for subdiffusion, the time derivative has some power. And today I would like to actually in a lot of biological systems, we can see the transition between these three different kinds of diffusions. Today I would like to discuss two examples of it. The first one is from subdiffusion, the transition from subdiffusion to normal diffusion. This is observed when people trying to look at water transportation on the protein surface. The second one is a transition from super diffusion to normal diffusion. This would happen for E. coli chemotaxis. So then I will go to the details of each of this transition. For this first one, subdiffusion, it's from water molecules. Actually, water is the solvent very important for the transportation of functional ingredients the water molecule can help to transport functional essential ingredients in our body. But it is well known that when water molecule diffuses in bulk water and near the DNA, RNA, or protein surface, the diffusivity is quite different. When the water molecule is near the protein surface, the diffusivity is significantly reduced. This phenomenon can be observed both by experiment and by NV simulation. This is a picture for when people when people doing the neutral scattering kind of experiment to look at the water molecule near some protein. Well, they can also theoretically do some NV simulation about it. Actually, these are a group of biophysicists in my institute. In 2018, they published a paper and report the really detailed measured about the diffusive behavior for water molecule near the protein surface. So what they observe is that in bulk water, it's normal diffusion. They just plot the time and versus the mean square displacement, and observe that in bulk water, the water molecule is performing normal diffusion. Well, near the protein surface, actually they tested in this 2018 paper, they tested two different kinds of protein and found that for both protein, when water molecule diffuses near the protein surface, the fractional power actually they are quite close to each other. Then we trying to look at this problem together, and recently they expand their experiments and this simulation and tested 8 different kind of proteins. For this 8, they choose these 8 different proteins. Actually, for them, their structure is quite different. Here is a picture about what happens there. Actually, this is the protein surface. The bacteria, the water molecule would just they can either near the protein surface and jump out to the bulk surface, to the bulk water, or they can transport near the protein. What they observe quite surprisingly that the diffusion power for all these 8 different kind of proteins are the same, no matter what structure the protein really looks like. So in order to explain this kind of universal subdiffusivity phenomena, they actually in the 2018 paper they already have a model which can be if we look at the trajectory of the particle, it behaves like this. Water molecule actually. They behave like this. They would wandering around some place for some time, then suddenly jump to another site, then wandering around here again, then jump to another site. So actually this process can be modeled by a continuous time random walk. But there are 2 ways to look at the statistics for this continuous time random walk. One way is to just trace each of the water molecule, then count how long it waits in each of the sites, then put all this waiting time together, plus the probability density function for all the water molecules. The other way is to sit inside one of the sites and wait until wait for the water molecule to jump into this site. Then record how long the water molecule waits in this site, and when one particle goes outside, after some time, another one will jump into the same site again. Then after you wait for some time, we can get the average waiting time for this site. This is called the basin waiting time distribution. This basin waiting time distribution is plotted in this red dots here. Well, for this, when the waiting time distribution by tracing all the water molecules is plotted by this blue dots here. We can see, actually, if you look at the result, we can see for the x-axis here. This is the x-axis is for different kind of protein. The y-axis is a power law, is a fractional power. We can see that actually, if we look at the basin waiting time distribution, actually it is different. It violates the power violates, which is unstable because the structure of the proteins are different. But if we look at the waiting time distribution of the water molecules, the violate much. They don't violate much. It looks like the fraction power is quite universal. Actually, this can be explained by this simple integration, because this P star is the basin waiting time distribution, while this P tau W is the particle waiting time distribution. Even though for the basin waiting time distribution can be quite different from each other. Well, I mean, quite different. Actually, it's not that quite different because it's just for different proteins. Here, for example, here, when the time is short or when the time is long, they are away from each other. But after the integration, this waiting time distribution for the particle, they become really close to each other. This work have recently been okay. I worked with this with my biostasis colleague, and recently the work has been accepted by physical review research. But actually the result is not that satisfactory because actually in order to explain the power law observed in the MD simulation and experiment, there is an assumption that the P star, the basin distribution obeys the power law decay distribution. But why is this? Actually, the model I showed just now is just an empirical model. There's no information at all about what happens inside each of the sites. And also there's no information about the space. But actually, their experimental data, they are able to get they can follow the trajectory of all the particles. So they have the information about what happens inside each of the site and what happens at different places of the protein interface. So this is a typical trajectory, like what I explained just now. This is each dot is the water molecule. It's just wandering around this site for some time, then jump to. I think this is the one is the place where it starts. Then it jumps to site 2. They're wandering around. You can see actually it's wandering around quite some time. Then go to another site. But for the model I showed just now, there's no information at all what happens inside each of the sites. There's no information is needed there. So, and in order to explain the experiment, there is an assumption there. The basin distribution obeys the power law decay. But why this happened? There's no explanation. It's just put as an assumption. The other observation is that actually when they measure the fractional power, it's only from time. The time scale is for short time scale, which is like this 10 to the power 2 until Zhang Yuan Zhang. He is a probabilitist in Peking University. That's why in this work, when we're trying to explain this, we use some probability too, but I should give all the credit to him that helped us to work this out. And Zhen Nanzhou, who is also in Peking University, together we're trying to explain why this proposal model hypothesis, why the waiting time distribution should be power law and why the transition should happen. So the model we use actually it's not complex at all. We only need to think about what happens inside one site because it's already proved that if the waiting time distribution inside one site is satisfied the power decay, then the overall population level behavior should be a subdiffusion. So if we want to see why the waiting time distribution is power law, we only need to look at what happens inside one site. For inside one site, we can imagine this y as a space variable, while this s as a potential. It's clear this two-term, it's like the particles can wandering around some potential well. This is basically what explains that this strict term is potential well, that it should drive, the particles should be confined near the site while they are wandering around, so there is a diffusion. But they are able to jump out. When the probability that they jump out, if this y you can consider as a predation. If the predation actually depends on y and s, okay, it's a typo, I should put s as well. If y is larger, is away from the center, for example, away from the center, then it would have probability to jump out. If it's close to the center, then it will just stay inside the site. This is the meaning of this model. There is also a stochastic version of it. We can just think about x as the predation. If this x, as c as the predation, you can imagine it as not the distance. It's like it should be the distance of some area of this area. If the distance is positive, if this x is positive, then it should go to the 0 can be considered as the barrier for this area, and when it's positive, it can go outside of this place. But if it's negative, it will stay inside this area. But its position can wander around like this, controlled by this stochastic process. Actually, the stochastic model and the PDE model, we can get the equivalence between them to get the relationship between the coefficient of them. So why this kind of model can possibly explain what I showed just now? We can look at some simple example. We can just put this f to be 0 and this d to be a constant. Then the equation becomes like this, which is a quite simple one. But the number here have a jump. If we want to look at how many, the waiting time distribution for the particle, then we only need to look at this term. Whenever I move here, then this thing appears. Wait. So we only need to look at, we can imagine if initially there are a lot of particles here, and then this so this capital MT actually describes the rate of this, how fast this particle leave this site. We only need to look at how this capital MT decay with time, then know the waiting time distribution for the particles. Then if you have this in mind, actually, then the other calculations is easy. We just need to do Laplace transform for this simple equation. Use the fact that the lambda is a piecewise function, while the initial condition is the delta function for P. exact calculation to find out that actually the waiting time distribution, the waiting time distribution should obey some power law decay for this simple case. Actually, this idea, then in order to explain why it should have some transition, then we need to add the drift. The drift here, this f, in order to make the computation simple enough, actually we first try some piecewise constant case, which means that this drift is minus a small number when y is positive. When y is positive means that this small drift would drive the system to the equilibrium, which is y equal to 0. So this is why we have this minus f from here and the plus f from here. This is kind of like the potential well that would make the particle confined in this place. Well, the diffusion coefficient is still constant. Then we can do calculation for this. It's still a simple system, but with one additional small epsilon is a small parameter. One additional term. To do the exact calculation, we find out that this mt actually would have an exponential decay tail here. So if we plot this picture, it's like it will have first have a power law decay. Then at the tailpipe, when the time is long enough, it will become exponential decay. This kind of waiting time distribution would provide us the transition. It would provide us that for the short time, we can see the subdiffusion, where for when the time is long, then we will see the normal diffusion. So basically, this is what happens inside one side. This is a simple example that we use piecewise constant to get the idea what happens there. Of course, we hope to look at a more complex model. So if we go to the probability too, then the stochastic model, we just use OU process, which is the most well-studied stochastic process for probabilities. The only difference is that the jumping out the jumping out probability relates to the predation of the value of x. So by using probability, we are able to get that the probability that the particle wait inside this site for longer than t is less than some exponential function for when t is large enough. The meaning of this result, it means when the time is long enough, we can see the exponential decay tail, or the tail should be faster than exponential decay. Well, the second result is that when the time is between some constant and epsilon to the minus 1 half. Actually, this gives us a time scale. At which time scale we can see the power law decay. When the time is shorter than this number, then the probability that the particle wait inside the site is larger than a power law, some power of t. So actually, when the smaller the epsilon is, the longer we are able to observe some power law decay waiting time. But then this basically give us the transition time, at least some bottom line of the transition time of the power law decay and the exponential decay. So then we go to the TDE2, trying to prove the same result. Then the idea is like this. It's the same as the model I used before. The only difference is that we change the drift term into y instead of a piecewise constant, which will help us to make the calculations easier. The strategy is the same. It's just to do Laplacian transform but we need to split the interval into plus and minus, and and because of this the jumping velocity, jumping probability have a jump at 0 points. This two condition is just from the initial condition. Then we need to do some asymptotics. After do the asymptotics, we can get the same result as what we can get by probability 2. But because we do asymptotics, actually we can get something more. We can get exactly the power law decay. Which power is should be for the power law decay, and when the time is long for this